Okay guys, so here's our agenda for the day. Just so y'all know, I will be checking homework next class. You do have a quiz next class as well. And here's your unit test date. That is the September the 18th. That is you guys. So this is the day that we will have our test, unless we decide to push it back. But right now it's set for the 18th. So get that in your agenda. It's also posted on Google Classroom. So we have the notes video, which is what you're watching right now. And then we do have these 3 practice items. If you do not finish them, they will be for homework. And I will take one at random next class to grade and collect. The sub should be handing out your practice packet with these 3 items in it. And at the end of class, you will have 15 minutes to complete the exit ticket. Now the exit ticket should be done on your own. It should not be a partner activity. It will be done independently, so it should be quiet in here. Okay, so let's get started with the notes for the day. We are talking about Venn diagrams. Venn diagrams. So get that copied down. That's the topic of the day, Venn diagrams. So Venn diagrams are a visual way of displaying the relationship between different sets. So the types of different Venn diagrams that we have are 3 different types. We have an all, always, and every Venn diagram. And that's why my P is inside the Q. Whenever we have my sentence P, whatever that may be, say all dogs are mammals. So this P would represent dogs, and the Q would represent them being mammals. So all dogs are mammals. That's why the P bubble fits inside of the Q bubble. Okay? And so what we use for this is a conditional. A P implies Q statement. If we have a dog, then it is a mammal. So all elements of whatever the P statement is are also elements of whatever the Q statement is. Okay? The next type that we have is some and sometimes. So that's where we have the merging of the 2. So in this little section here, this red section that I'm highlighting, in between the 2, this is an and statement, P and Q. That's what they have in common. Whereas the whole thing, this whole big bubble, either Q or R, or excuse me, P or Q, that is my or statement. Okay? And the last type is never, no, or none. And there's no relationship between P and Q. So that's why the bubbles are completely separate. So there are your 3 different types. So let's go down to some practice problems. Draw a Venn diagram to represent each statement. Okay. Some students who take chorus also take band. Well, this is my key word there, some. Some students indicates that we have a merge of the 2. So some students who take chorus for C, also take band. So we have the chorus bubble and the band bubble, and the some students would be right here in the middle. Number 2, no perfect squares are prime numbers. Well, this is my keyword, no. So that's going to be the 3rd option that we had, where no perfect squares are prime numbers. P for prime. Okay. So there's my Venn diagram. The last one, numbers divisible by 6 are always divisible by 3. So here's my keyword, always. So that indicates to me that these should be a bubble rest inside another bubble, and I just need to figure out which one's the inside and which one's the outside. So numbers divisible by 6 are always divisible by 3. So the divisible by 6 is the more specific type, divisible by 6, because that's more specific than my divisible by 3. Divisible by 3. Okay. All right. So those were the 3 that I'm doing. So take a moment, somebody pause the video, and you guys are going to try number 4, 5, and 6. And when you come back, I'll have the answers shown. So there you go. There are the answers to 4, 5, and 6. The natural bubble is resting inside the whole numbers bubble. In number 5, it's a merge of the 2. And in number 6, they have nothing to do with each other, so they are separate bubbles. Okay? So the last part that I want to talk about is sometimes I'm going to ask you to shade in the regions that I'm describing. So in number 7, I'm describing just Q. So I'm looking for where Q is on this Venn diagram, and I'm shading in the whole Q bubble. Okay. The next part is P and Q. So the and tells me that they're merging together, so the place where that exists is right here in the middle. A P and Q is right in the middle. We already talked about that on the front. So here's some more examples. Go ahead and take a minute and do the P or Q, shade it in, and do P and not Q. So go ahead and try those 2. Pause the video. When you come back, there will be the answers. Okay, so here are your answers. P or Q, that's the whole thing shaded. But number 10, P and not Q. So I should be shading in the P section, but I have to take out the part that includes Q, which is that middle section. Okay? So the last thing is describe each diagram using a conditional or a compound statement. So what's happening in the first one? That is a sum statement, and we need a conditional or compound. So remember, a conditional is a P implies Q, and a compound is when we use the and or the or symbol. So I have to use one of these 3. So in this case, I'm going to use an if-then. If an angle measures 60 degrees, then it is an acute angle. The if part, the hypothesis, an angle measures 60 degrees, that comes first because as a result of it being 60 degrees, it is acute. Okay. I'm going to skip number 12 because you guys are going to do that on your own. Number 13, however, what we have shaded is between the volleyball and the piano. So we would say some people play volleyball and, because remember the and is where they merge, and they take piano. So again, we're going to pause the video. You guys are going to try out number 12 and number 14. So the answer to number 12 should be if an animal is a beagle, then it is a dog, because beagle is more specific than dog. Number 14, the months with 31 days and do not start with a J. That is what's highlighted. That's what we're describing. Go ahead, pause the video again. We're going to try out 15 and 16 this time. Go ahead, pause it, try it, done. So there are the answers to 15 and 16. Students who are freshmen and do not take an art class describes 15. And numbers that are multiples of 7 or are even numbers describes number 7 or 16. Okay. We do have one more topic to talk about. Properties of equality. So we have the addition property of equality, the subtraction property of equality, multiplication property of equality, division property of equality. So let's go through the formal definitions for all of these different properties. starting with addition property of equality. So if we have some number or statement, if A is equal to B, then we can add something to A, and we can add that same thing to B, and the two equations, the two sides of the equation are still equal. With my subtraction property of equality, it's the same thing. If you have something, A, equal to B, then if you take away a value, it'll be the same if you take away that same value on the other side. Okay. So the third one, the multiplication property of equality, it's still the same concept. If you have one side equal to another, then if you multiply the first side by a scale factor, it should be the same if you multiply that scale factor on the other side as well. The last one, division property of equality, if you have A equal to B, and you divide A by C, that'll be equal to the same thing as long as you're dividing by C there as well. Okay? The distributive property. Distributive property. Hopefully you covered this last year in algebra, or maybe even your like 6th grade math. But remember that the distributive property, you take the number that's on the outside here, and it gets distributed, it gets multiplied with everything on the inside. So if you're given A times the quantity, B plus C, then A times B plus C is still equal to A times B plus A times C. And that is the distributive property. Okay. The reason why we're doing all of these properties is so that you can basically justify your reasons for doing things in algebraic problems. So it's just a reason why. So, moving on, we know the substitution property. Hopefully we know the substitution property. If you have A equal to B, then A may be replaced A may be replaced by B in any expression or equation. Okay? So all you're doing is just substituting it in, you're just plugging it in, you're replacing it. My reflexive property, excuse me. This states for any real number A, the reflexive property says that A is equal to A. So a value will always equal itself. A reflexive property, think of it like your reflection. You look the same. So A is equal to A. That's all we got there. The symmetric property is a little bit different. If you have some value A equal to some value B, then we know that B is still equal to A. All I'm doing is just flipping the order of things, just flipping it around. The last property is my transitive property. So the way that the transitive property works, if you have a value A, it's equal to B, and you have some B that's equal to C, by the transitive property, logically, if A equals B and B equals C, then A should equal C. So there's your transitive property. Okay. So hopefully you got all those copied down. And we'll go ahead and move on to using the properties of equality. Properties of equality can be used to justify steps in solving an equation. So something that we do a lot of in the logic unit are making proofs. And a proof is just you proving how you got to the end of your equation, or other different types of scenarios, but right now we're just doing an equation. A common format to use to organize a proof is the two-columned proof. So we use this, the two-column proof. On the left side of the two-column proof, we list these statements. Or what those statements are, they're just basically steps. Steps that you're using to solve the equation. On the right side of the two-column proof, we are listing the reasons. So we're listing the reasons why those steps work. Okay? So what can be used as reasons? What can be used as reasons? Well, we can use any different property that we just talked about. We can use any definition we know of. We can use any theorem. And we can use any postulate. So we haven't talked about theorems and postulates yet, but we will when we go back to the first unit, the geometry basics unit. Basically, theorems and postulates are just things that have been proven over time that have proved too difficult for you to reprove in your own proof. There was a lot of proofs, but anyway, so we're using the two-column proof, fairly simple. Here I'll give you an example. So I start off with a given. My given statement is that 4x minus 1 is equal to 27, and it's asking me to prove that x is equal to 7. So since this is an algebraic proof, I need to go through and do all of the steps. You do not do more than one step or one solving in one step if they have different reasons. Okay. So I'll go through that in a little bit, but basically you just do one step at a time. Even though it's tedious, you are solving out the problem as if you were teaching it to somebody that's never solved an equation before. So step one is to write out your givens. And that's always going to be step one. You always want to write out your given statement, and the reason for it is because, well, it was given to you. So the second step here is, what did I do? Well, I technically added 1 to both sides, correct? So that brings me to just having 4x equal to 28. Now I need to have a reason for why I went from step 1 to step 2, and that reason is the addition property of equality. The addition property because I added 1 to both sides. Now from step 2 to step 3, what did I do? Well, technically I divided by 4 to yield x to equal 7. So what I did from step 2 to step 3 is I used the division property of equality. And there we go. I proved that x is equal to 7. My last step should always be what they want me to prove there. Okay. So I'm going to give you a couple more. And I already did most of the workout there. So go ahead and try number 1 and number 2. Or excuse me, number 2 and number 3. And I'll come back with the answers after you have paused the video and tried it. Alright, so here's my answers. In number 2, I start off with my given, I use the subtraction property of equality, and then I use the multiplication property of equality. In number 3, I start off with my given, I use the distributive property of equality, then the subtraction property of equality, then I use the division property of equality. Go ahead and try. Am I going to be able to have enough room? No. Go ahead and try number 4. Pause the video. I will come back with the answers. Okay, so here's the answer to number 4. I start off with my givens. Remember, we only do one step at a time. So I take away the 6x from both sides, and I'm left with 7 equal to 2x minus 17. I use the subtraction property of equality. I get the 17 to the other side. That's the addition property of equality. And last, I need to do a division by 2 on both sides, and I use the division property of equality. And a lot of you may be thinking, well, technically I proved that x is equal to 12. No, you did not. You proved that 12 is equal to x. And yes, it is the same thing technically, but logically we read off as it's told. It needs to match verbally exactly as they asked you to prove. So 12 equals x is not the same logically as x equals 12. So you need to flip it around, switch sides. That's why we use the symmetric property of equality. Okay. The last one here. Go ahead, this is the end of the video for the most part. Try it, pause the video. I will have the answers back up when you come back from pausing it. Okay, so here are the answers to number 5. The first, of course, we have our given. The second, we use the distributive property of equality. And notice how I did this distributing and this distributing. It's okay to do that because it has the same reason. I can do both of those steps in one line because they have the same reason, the distributive property. Now to get from step 2 to step 3, all I did is I combined my x's on the same side. We don't really have a formal reason for that, so if you said simplify or combine like terms, both of those would be completely acceptable. To get from step 3 to step 4, we use the subtraction property of equality. From 4 to 5, the addition property of equality, and from 5 to 6, we have the division property of equality. Okay, so at this point, I would like the sub, please hand out the packets to each student. So guys, in your packet, you have 3 different sheets. The first sheet is a truth tables review. The second is going to be a Venn diagrams practice sheet. And the third is a proofs practice sheet, what we just did. Now in the proofs practice sheet, you will be given equations like this, and you will be given a blank table. So none of this would be written in here. They would all be blanks. So what you need to do is you need to actually solve the equation, and you need to give the reasons for each step. Remember, if it has more than one reason, you cannot do it in the same step. And if you need additional lines, like the grid is not big enough, if you need more boxes, you're more than welcome to add on more. And I think that's pretty much it. So go ahead, finish those up. What you do not finish is for homework. So give it your best shot, compare answers with each other, make sure that you're understanding it, and come to me with questions when I am back on Tuesday.